distribution of beta particle. The energy distribution of beta particle is continuous in nature, but in alpha particle case, the energy distribution of alpha particle is discrete in nature. Please do remember. This is energy distribution is discrete for alpha and continuous for beta particles. So now today let us discuss with the topic the Fermi's theories of allowed beta decay. Allowed beta decay, as you know, for the alpha decay, beta decay and gamma decay, some certain rules and regulations are there. The element, if you kept one element to undergo the beta decay process, it must obey some rules and regulations. Then only that element is allowed for beta decay process. That's why that what we call it as Fermi's theories of allowed beta decay. So it gives a mathematical expression for the energy distribution of the beta particles. Sorry, 1 minute. So please stay on. Okay. So now we'll start with Fermi's theories of allowed beta decay. The physical properties of neutrinos are such that they are very difficult to detect since they carry no charge. They cannot produce ionization in matter, so the usual methods of detection of charged particles cannot be applied for their detection. Since they are practically massless, they cannot transfer energy to any other particle by elastic collision. Hence, the method applicable in the case of detection of an electrically neutral particle like the neutron cannot be used in their case. There are reasons to believe that the sun emits a huge flux of neutrinos every day. For this reason, the earth is being incessantly bombarded by neutrinos. It has been estimated that about 10 raised to 14 neutrinos pass through the human body per every second. However, the probability of their interaction with the atoms in the human body is so small that not even one such collision takes place in a whole year. As stated before, there was no direct evidence for the detection of the neutrino for a long time. Finally, in 1956, two American scientists, F. Raines and C.L. Clone Jr., he was the junior of F. Raines, were successful in detecting the neutrino directly. Their experiment will be discussed in later. So see, as stated before, the neutrino and its antiparticle. See, in the universe, every particle which is having its anti-particle. So neutrino and antineutrino, the former is emitted at the time of beta positive decay and electron capture process, while the latter is emitted at the time of beta negative decay. So we can represent these processes symbolically as follows. See here. You can see equation number 5.63, 5.64 and 5.65. Okay. So in the beta negative decay. So in beta negative decay, so equation number 5.63, as you know, the jet is increased by 1 during the beta negative decay process and anti-neutrino particle is liberated. Okay. Liberated. And in beta positive decay, so C 5.64, so here the Z is decreased by 1. As you know, here neutrino is emitted and electron, as you know, the beta positive decay process and electron capture process is similar in nature. Here also the Z is decreased by 1 and neutrino particle is emitted. So during the beta positive decay and electron capture process, neutrino is liberated, and in the beta negative decay process, the anti-neutrino is liberated. Okay. The neutrino and antineutrino are both massless and chargeless particles with the sorry for the disturbance. The neutrino and antineutrino are both massless and chargeless particles with the same intrinsic spin 1/2. So it is believed that the difference between them lies in the fact that the spin vector S of the neutrino is antiparallel to its linear momentum, while for the antineutrino the two vectors are parallel. So as shown in figure, neutrino and antineutrino. See here, neutrino and antineutrino. See the figure here. So a figure. So A and B. Okay. The neutrino and antineutrino are both massless and chargeless particles with the same intrinsic spin. It is believed that the difference between them lies in the fact that the spin vector S of the neutrino is antiparallel to its linear momentum P, while for antineutrino the two vectors are parallel. So here antiparallel, here parallel. So I have shown in figure 5.13a and b. Okay. Now we shall see that weakly interacting particles like the electron, positron and neutrino and antineutrino belong to a class of elementary particles called leptons. Okay, so in the third semester you learned regarding the elementary particles. So that is elementary particles. So elementary particles are divided into two groups, as you know, leptons and hadrons. Okay, leptons are very point particles. We cannot describe the structure of these particles. Electron, positron, neutrino and antineutrino belong to a class of elementary particles called leptons. It is usual to associate a lepton number L with them. For the electron and the neutrino, we put L is equals to +1. For the antiparticles, positron and antineutrino, we put L is equals to -1. So that is leptonic number for neutrino and antineutrino, positron and antineutrino are -1. Because the neutrino which is having the leptonic number +1, hence its antiparticle which is having -1. At the time of beta decay, there is a conservation of the lepton number, which means that L remains the same before and after the decay. There is a conservation of the lepton number, which means that L remains the same before and after the decay. For example, in beta negative decay, L is equals to 0 on the left side of equation 3. You can see the equation 3. Equation 3. So beta negative decay. Here, L is equals to 0 on the left side, LHS side. On the right side, the total lepton number is 1 minus 1 equals to 0 here. So leptonic number here equals to 0, and here, so this is 1, and for the antineutrino leptonic number is -1, 0 and 0. So leptonic number is conserved in nature. So the lepton number is conserved. Similarly, for the beta positive decay, in the case of electron capture decay, L is equals to +1 both on the left and right sides. So lepton number is conservation is satisfied. So here see, L equals to 0, again +1 -1 0 +1. So here 1 and here in. So here in all the three cases the leptonic number is being conserved in nature.